Welcome, students. Sorry I can't be here today. I have a field trip. So I figured, because I can't be here today, that it would be good to make a video where I go over the Unit 3 test review. Your solution key is already posted to Google Classroom, but now hopefully this supplemental YouTube video helps you as if I was here today. So let's take a look. The first 6 questions or exercises on our test review ask us to match the derivative with each function. It might be easier to actually match the function to the derivative. So let's go through the first 6 and match them to the derivative. In the first one, you'll notice that we have a positive slope of tangent lines, then we have a 0 slope of our tangent lines, and then we have a negative slope. You'll notice that down here it's a little bit of a greater positive, where this is a lesser positive. This is a lesser negative with a greater negative. So when we take a look, the only one that will match up with that is number 5. Again, we have our greater positive, a greater negative, along with our 0 that happens at the location x equals 0. We also have all positive and all negative. So it all matches up. All right. So the answer to 5 is going to be A. B, we have, it looks like a sine function. It's actually negative sine. So you'll notice we have a positive slope, and then a 0, then a negative slope, then a 0, then another positive slope. The only thing that oscillates like that is number 6. We have a function above the x-axis, which is positive. We have one below the x-axis, which is negative, and then we have one above the x-axis, which is positive. So it matches up to all those pieces, along with the fact we have 2 zeros, which happen here and here. So looks good. It's going to be B matches up with number 6. Just going to clear these out. C. C is going to be similar to A. In C, we have a negative slope, and then it becomes 0, and then it becomes positive. Again, we have our greater negatives and our greater positives. It's going to be a linear function. So when we match that up, we have, in number 2, we have our greater negatives, we have our greater positives, we have negative and positive along with 0 happening at about negative 1/2. If we look here, our our 0 slope happens at negative 1/2 as well. So C will match up with number 2. Let me just clear this out. D. Prior to 0, we have all positive, and after 0, we have all negative. We'll never have any 0 slopes. So when we go to match it up, number 4, D will match up with number 4. All positive slopes, our function's always above the x-axis, and all negative slopes always below the x-axis. And again, no zeros are seen. E is unique. It looks like we have a corner or a cusp. In this case, we're going to have a corner. We're just going to have differing derivatives on both sides. There's an immediate change here at negative 1 and an immediate change here at 2. We have a slope of 0, and then we have alternating negative, positive, negative, positive. So this is the only one that it matches up with. At negative 1, you have that immediate change in slope, and at 2, you have that immediate change. You have that same 0 that happens at 1/2. You have all negative, all positive, all negative, and all positive function. Again, not a cusp, because the derivative would go on forever. It would look something like this. But because it just differs, and it can be calculated depending on which side we come from, It's just a corner. So 3 matches up with E, and the last one is F. This one has 3 zeros, 1, 2, 3, at about -1.5, 0, and 1.25 or so. It has all negative slope, all positive, all negative, all positive. So F is going to match up with number 1, all negative function, all positive function, all negative function, all positive function, and 1, 2, 3 zeros. All right, and that is it for 1 through 6. Continuing on to number 7. I've already calculated all of the slopes, so we just need to graph them, and our placement that are held are -6 and -4. So we graph 3 as a constant between -6 and -4. We graph -2 from -4 to -3. We graph 2 from -3 to -2, and we see all of that being graphed here. I'm going to skip this one for right now. From E to F, we have between 2 and 3, you see a slope of -1. Between 2 and 3, we see a slope of -1. So a constant -1 slope. Between 3 and 5, we see a slope of -2, so that was graphed. Then a slope of +1 between 5 and 6. I'm going to clear all this out, all the lines I drew, and now let's focus in on this parabola. This parabola has a equation of y equals x squared. Now, how did I know that? Well, just square 1 and you get 1, square 2 and you get 4, square -1 and you get 1, square -2 you get 4, square 0 you get 0. So the inputs and outputs all match up to the function that I just wrote. The derivative is going to be y prime equals the derivative of x squared is 2x. So that's the line that will represent my slope at every single location. So graphing 2x, this equation is 2x plus 0. So here I have a y-intercept of 0. I go up 2 over 1, up 2 over 1. Going in the reverse order, I go down 2 over 1, down 2 over 1. But if I go from left to right, it always goes up 2 over 1, up 2 over 1. So I graph that between -2 and 2, which is where my parabola begins and ends, again with open circles on the endpoints. The reason for all the open circles on the endpoints is because we do not have derivatives at all those. Those are all corners. So the locations where my derivative does not exist, which is this question right here, between -6 and 6, not including -6 or 6, just between, is at the locations B, C, D, E, F, and G, which are at x equals -4, -3, -2, 2, 3, and 5. All right. I note here, whoops, I don't know why I did that. All right. In number 9, we're given a lot of information, whether we realize it or not. We were given that an input of -2 has an output at -6, and at the same location of that input, there is a slope, or derivative, a slope at that location of 4. So I know that x is -2, I know that y is -6, I know that my slope is 4, and my perpendicular slope at this moment in time is -1/4. I don't know what the actual function looks like. What I know is that I need to find a tangent and a normal line at that location. So I chose to use slope-intercept form. You can use whatever form you want if point-slope makes more sense. but I'm going to substitute in my x, my y, and my m to solve for my b. After some algebra, I get b is 2. So my tangent line, I get the equation 4x plus 2. In my normal line, I use a perpendicular slope. I use the negative 1/4 with the same x, the same y, and after solving, be careful here, when I have a negative 6 and I have plus 1/2 plus b, equals 1/2 plus b, when I take away the 1/2, I'm taking away 1/2 from negative 6 already, so I get negative 6.5. Do not mess that up. I see students tend to mess that up. They get 5.5, or negative, I apologize, negative 5.5. So be careful with that. Kind of like on this one, when you add 8, you're going to get 8 minus 6, which is 2, or negative 6 plus 8, which is 2. So be careful on your negatives and your positives. So both equations are listed on your answer key. All right. 10 through 13. I used both the definition of the derivative and the alternate definition to model these. I want you to be familiar with the definition, but I think I'm going to allow you on your assessment to calculate it using derivative rules, seeing as we already know them. You can definitely verify both using derivative rules. I'll just walk you through the algebra that I performed. So the first thing I did was evaluate each function here, f of x and f of x plus h, and I substituted them in for wherever I saw, wherever I had f of x plus h minus f of x all over h. Then I was very careful to find a common denominator. This one is missing a multiplication of 8x. This is missing a multiplication of x plus h. So by performing those, here's my new x's, here's my new x plus h's. You notice I'm multiplying each by 1. X over x is 1, and x plus h over x plus h is also 1. Then I distribute. I'm very careful to distribute my negative across to my x and my h to make sure I have negative x minus h. Now that I have a common denominator, I'm able to move the h into the denominator of the other one by multiplying by the reciprocal. Now, really, that's going to move the h right here, which then it reduces with the h. I didn't show that work. I immediately came to this step right here where the h canceled out. But in theory and in reality, h is within the denominator now, or can be within the denominator of the top function, because this I can look at as h over 1. Multiplying by its reciprocal would be 1 over h, leaving it in the denominator of the function that's currently within the numerator of this greater fraction. All right. After that, we are left with negative 1 in a numerator. We now have the ability to evaluate h as it goes to 0, and I get negative 1 over 2x squared. This is no different than if I use the quotient rule. So focusing on the quotient rule, I would move my x to a numerator. Using the quotient rule, it would be denominator times derivative of numerator minus numerator times derivative of denominator. It will yield the same exact result as negative 1 over 2x squared in any order, whether the negative is attached to the 1 or out front of the fraction. Evaluating at the location 2, which is what it asked me to do, I will get negative 1/8. Doing the same thing using the alternate definition, it involves factoring out an a minus x to reduce that, or I apologize, x minus a, to reduce that from a denominator. Again, you can skip through this part. If you're not interested, you can just do the quotient rule. So feel free to fast forward this YouTube video. Here I substitute in what I need and I find my common denominator, which leads me to 2xa. This a minus x can go away with the x minus a if it was in the opposite order, if x instead was positive and a instead was negative. So that can be done by factoring out a -1. You'll notice that's what I did right here. I would draw that negative, putting it in the correct order. I also rearranged the order, making sure that it was able to be simplified with the item below. Let me clean this up. Okay. As a result, I'm left with -1 over 2xa, and x approaches a, which gives me a times a, or a squared. Just because approaching a doesn't mean I have a different variable here, because I'm actually evaluating a as x. So I can just simply replace it with, as you see here, with x, yielding the same result. Again, quotient rule works here. Not only does quotient rule work, but the negative power rule works. If I were to move x up into a numerator, starting at the beginning, I would have 1/2 times x to the -1. Deriving that would give me 1/2 times -1 x to the -2. And then moving it back down to the denominator would leave me with -1/2. -1 over 2x to the 2x to the 2, which is exactly what I have. Evaluating this at the location 3 would give me a slope of -1/18. Again, these 12 and 13, you can look through my work. I don't think I need to go into detail. I think you can follow it. But simply speaking, if I just use a power rule, I should get, for a derivative, I should get 2x minus 5. So f prime of x will be equal to 2x minus 5, which is what I have as a result using all of this definition, 2x minus 5. In both, whether I use the regular or the alternate, I still get 2x minus 5. Evaluating that at 2 would give me -1, and evaluating that at 1 would give me -3. All right, a lot of work. I would probably stick with the power rule again. I think Mrs. Garcia and I have come to an agreement that if it's simple enough to use your rules, you should know the definition by now and understand the definition. But if you would like to just use your rules for differentiation to solve, that's fine. Either way will be acceptable. Okay, this one. The purpose of this question was to really challenge the ideas of derivatives that don't always follow the basic routine. So normally we get a tangent line that's y equals mx plus b, and we get a nice line like 2x plus 5 or -1/2 x plus 6, something along those lines. What we'll notice in this equation is the particular points that I ask you to find right here, -1, 1, and 0, all have unique characteristics. -1 and 1, these two, are both horizontal tangents, looking like this, which means that they're normal lines, the ones that form right angles with them, the normal lines, are vertical. As a result, you will literally get x equals -1 as a vertical line. In this case, x equals 1 would be the vertical line for x equals 1. And then whatever outputs you have at that location. So y we have as -2, and y we have as 2. So whenever we have a horizontal or a vertical, when we have a horizontal tangent with a vertical normal, or a vertical tangent with a horizontal normal, we will always have, our answers will always be in the form of our coordinates and their equations, so x equals -1 and y equals -2. Let me explain quickly the work that went into finding this. First, I started by using the quotient rule, which you see here, the denominator times derivative of numerator minus numerator times derivative of the denominator. Extremely important to keep that negative where it is and distribute it to both terms. Without that, we will not have the correct result. If you would like to use brackets, that is fine, to make sure that you take away the entire x squared plus 1, making it negative x squared minus 1. After simplifying, I'm left with this result. I then chose to evaluate that result, x squared minus 1 and x squared divided by x squared, at all locations. So, well, I did it at -1, and you see that I get a slope of 0, which means that you get a slope of 0. So you know that the perpendicular slope is undefined. Same thing occurs here. We get a slope of 0, and we know that the perpendicular slope is undefined. What's interesting is when I go to evaluate the point 0, we get a denominator. Think about when I do 0 here, 0 squared minus 1 over 0 squared, I get -1 over 0. That cannot be done. There is no domain there. There is no domain in the original function as 0. There is no domain of a derivative at that location. So the derivative simply cannot be done at all. I put none for either one of these. The function does not exist here, so nor can its derivative. Remember, derivatives imply continuity, so if there is no derivative, then there is no continuous function at that point. So now I have my equation. My slope is 0 and 0 and undefined and undefined. So we are now very close to figuring out our tangent line and normal line. I'm going to evaluate, over here, I'm sorry, I kind of skipped this, but I evaluated what my outputs were at each location. I have no output at 0, and I have outputs at 1 and -1. So that's where I first came up with the points that you see in this highlighted blue. So I have my outputs. I now calculate my tangent line at -1. I have to do this 3 times, well, really 2, because one of them can't be done at all. So I evaluate the tangent line. I use my x and y and my m, and I get y equals -2. So that's my y equals -2 is at x equals -1. So both of those, x equals -1, y equals -2, are the equation of my tangent line at the location of -1. Again, the coordinate and the equation are synonymous. They are the same. So then I go to evaluate my tangent at x equals 1, and I get 2. So that's my x equals 1, y equals 2. I also I tried to show you that when you put an undefined slope in here, that's not going to work out. You won't get a result. Therefore, this is function undefined here for both. No function exists. All right. Moving on to 15 through 18. I put a note here that I showed you how to calculate them by hand, and I will check them using nderiv function in my calculator. If I say to just calculate them using nderiv, just be careful, parentheses, and evaluate. Here I did in number 15 the product rule, and I evaluate at -3, getting 36. Be very careful with algebra. Make sure you evaluate using nderiv, and both are stated here, or anything equivalent. So I would have marked off, if it involves a fraction, 6 is the same as 12 over 2, so that's equivalent. In number 16, again, here's a better example. here's the derivative. You could leave that as your answer if you'd like to, or you can simplify. Regardless, they're both correct. They're both equivalent. So I put the equivalent on the line, and then I evaluated at the location -3 to receive the solution 45. You do not need quotient rule. You do not need quotient rule. I know it shows 4, 3, and 2 in the denominator, but think about it as 5/4 times x to the 4th. 5/4 times x to the 4th. It's 5/4 as a number times x to the 4th. So you can derive just x to the 4th. You'll notice I left it in fractional form and I simplified out the parts that reduce. That was purposeful, leaving me with 5x cubed plus 4x squared minus 3x plus 1. Again, anything equivalent would be correct. Next, evaluating that at -3, I get a result of -89. Can you use quotient rule? Yes. Do you want to? No. No, no, no. It would just cause more work than you need. This one, 18 can be monstrous if I don't simplify it first. Yes, we are allowed to simplify because the result of simplifying will give us the same derivative. Because writing an extended expression or equation has the same result other than the discontinuity at -1 that I'm ignoring, which is still there, which you still see actually right here. So I'm not really ignoring it. It still shows up regardless of how it shows up. Simplifying this will make it much easier to derive because you don't know yet the chain rule. And this involves chain rule. X plus 1 squared involves chain rule, or it involves distributing and then using the power rule, which can be something very, very intense. You'll have x squared plus 2x plus 1, and then you'll have to derive that, and you'll have to square that as a result. It's going to be pretty messy. Factor out the numerator, rewrite the denominator in factored form, and then simplify out the expressions that reduce out. Then use your quotient rule. Denominator times derivative of numerator minus numerator times derivative of the denominator. And do not forget, all over the denominator squared, but do not forget to distribute that -1 to both the x and the -1, making it -x plus 1. Simplifying will give me 2 over x plus 1 quantity squared. Evaluating at -3 gives me that value of 1/2. Again, anything equivalent would be okay. So if you feel more comfortable leaving it like this, then leave it like that. And then just evaluate. And those are my results. Moving on to number 19 and 24. We are looking for issues that lie in the derivative. So for instance, this one has a derivative that goes vertical. It has a positive slope from both sides regardless. As I move, these results will go vertical. And because they're both positive, it's vertical tangent, not cusp. The location occurs when x is 0. Again, x equals 0s. This one, number 19, there's no issue. It never goes vertical. It never has a problem. It looks very consistent. It's simple. There is no issue. So do not write the number 0 here. That's not the result. 0 is a location. You have to use NA, none, or not, no location. Anything else, do not use the number 0. 0 is a location. So differentiable on all domain. This one, issue, happens right here at 2. There is a corner. the derivatives differ. Prior to it's -1 exactly, and after it, it's +1 exactly. So the location in question, the location that causes me an issue is 2, and it's a corner at 2. Number 22. This one is a corner. Although it might look like a cusp, the derivative on both sides, and you'll have to graph this to see it, will look something like this. From -1 to 2, from -1 to 2, it will look something like this. With a positive slope, and then a negative slope with a 0 right here. And then after that, it will have an extreme positive and an extreme negative. But they don't go to infinity or negative infinity. They just have differing slopes. Graph it on your graphing utility if you need. The locations are at -1 and at 2, and it's a corner for both. Here, the derivative would cause an issue at 0. It is a cusp. As I get closer here, it's negative, and it goes to negative infinity for a slope, and this slope goes to a positive infinity. Because they differ, we have a cusp at 0. This one, because the original function is discontinuous, there's an issue right here, right? Because of that, we use the term discontinuity, and it occurs at 0. The derivative on both sides is 1. It has is 0. It has a slope of 0, slope of 0. If I graph its derivative, it looks something like this, right here. But the issue, again, there's a 1 moment in time gap, and it happens right there. There's a hole at 0. All right, we're almost done. In exercise 25 and 26, determine if the function is differentiable. The only issue caused is at 1. 1 minus 1 is 0. Even if I remove it, there is still an issue at 1. We have to account for that. So is it differentiable at 1? No. Why? It's a discontinuity. How was I able to find it? I removed the discontinuity right here. So I immediately know it's discontinuity. It's not going to be, there is no derivative from one side or the other. There's just one little issue there. There is no corner, so the derivative is not going to look like this. There is no cusp, so the derivative is not going to look like vertical tangent. I apologize. There is no discontinuity, so the function is not going to have a derivative that has a hole in it, and then it's not a corner, so it's not going to have a derivative that looks like this, where they differ. 26. The issue, there is an issue, it's at 0. 0 to the 1/3. Again, the 1/3 function looks like this. 1/3. Kind of the flip of x cubed, right? There's definitely a vertical tangent there. So the answer is vertical tangent and 0. However, right, there's a vertical tangent at 0. So the answer would be no and vertical tangent. However, that's not the point in question. The point is at 2. This function's okay everywhere else but 0. So see how it's okay at 2? I know it's not the same exact graph, right? So we would have to graph it to see what it looks like, but we know that the only issue here is at 0. It's not x minus 2 to the 1/3. That would cause me an issue at positive 2, because 2 minus 2 is 0, and that's the cause of the problem. So, because of that, the answer is yes at 2, and we're just going to use the end derivative in our calculator to calculate that. Don't forget, you enter d dx. You can enter in 2x to the 1/3. Be careful what parentheses may be around that one. Take away 6, all with respect to x equals 2. We get a result of approximately negative 3.48. If you have an old calculator, you'll calculate it as 2x to the 1/3 minus 6. You'll definitely have to use parentheses for this one. Actually, it will look like this. It will look super old. You'll say n deriv, parenthesis, 2x caret 1 divided by 3, just like that, minus 6, comma, define variable x, comma, define number of variable at 2. That's the old notation if you have the old calculator, the old software on the calculator. All right. Know that you have the ability of calculating multiple methods. Here, simply, I did the quotient rule on the left, and on the right, I decided to use the negative power rule, knowing that 1 over 2 is the same as 1/2, and separating that idea from x cubed. Moving x cubed up to a numerator gives me x to the negative 3. I derive it and get negative 3x to the negative 4, and then I move it back down in the place where it belongs in the denominator to make it a positive exponent, and they are the same regardless. So using the quotient rule or using the negative power rule, and I put that in the method column. Either one is right. They are both the same. Answer, not the same method. All right, find the third derivative. I think this is our last, nope, we have another page. Last question on this page. The first derivative, drop it down. The second derivative, drop the exponent down again. And the third, drop it down again. All being products of one another. So x to the 6th becomes x to the 5th, and so on. I think this one's pretty explanatory. As a result, these two numbers right here won't exist by the time it's all done. If I keep going, this one wouldn't exist afterwards, and so on. Okay. These last ones, there are a lot of them, but I want you to notice at the bottom here, 2u plus 6r, I already calculate 2u here, and I calculate 6r here. So you really don't need to do the last three. I kind of made them a combination of derivatives that are above. So the first one, 2u, I'm going to get 2u prime. The second one, 4v, I'm going to get 4v prime. And the third one is 6r, I'm going to get 6r prime. Using that information, I substitute in for u prime, I put in 6. For v prime, I put in 3. And for r prime, I put in negative 2. And evaluating all those, I get nice numbers like 12, 12, and negative 12. The second one, u over v. This is in the order we were introduced, so be careful. Just because I know the quotient rule is denominator times derivative of the numerator minus numerator times derivative of denominator all over denominator squared does not mean that it follows a pattern VUV, VU minus UV. It really depends on how these are listed. So if I list them differently, like V and U, then that's going to change the order in which they show up. So memorize it in terms of denominators and numerators instead of letters. Oops. So yes, denominator times derivative of the numerator minus numerator times derivative of the denominator gives me v u prime minus u v prime all over v squared. Pulling out all those pieces, v is negative 1, u prime is 6. Take away u is negative 4, and take away, and v prime is 3. Doing out that algebra gives me a result of, v squared. V squared is going to be negative 1 squared. So as a result, I get 1 as a denominator, so negative 6 plus 12 is 6. This denominator, again, it's r minus 1 over v. R becomes r prime. Negative 1 becomes 0. So if it's in the numerator and you're using just the numerator, you're going to be using r minus 1. But if if you're deriving the numerator, it's going to be r prime. So that's the only tricky thing here, is that negative 1 will stay if it's not being derived, and it will disappear if it is. So I get denominator times derivative of numerator, r prime, minus numerator, r minus 1, times derivative v prime. Think about, again, r minus 1 as being the function, take away 1 from it, which is okay to do. If it has an output at 6, take 1 away, it now has an output at 5. It is a translation 1 unit down. All over v squared, the denominator squared. Evaluating will get you negative 1. Be careful again. You have 2 minus 1, which is 1. 1 times 3 is 3, but you're taking it away. You have to make sure you distribute that negative. Here, denominator times derivative of the numerator. It's the sum of u and v, so it's going to be the sum of u prime and v prime. So r times u prime plus v prime minus u plus v times derivative of r, the denominator, all over denominator squared. After calculating the math and being extremely careful, I get the result of 2. The last ones, you can do them out. You can do 2u prime plus 6r prime. The 2 and the 6 stay because it's multiplying the function, which is different than adding or subtracting from a function. A vertical shift, up or down, plus or minus, will not change the derivative. However, multiplying a function by a number like 2 or 6 will have an ultimate influence on the derivative. That's why the 2 and the 6 still stay around. We don't need to evaluate that, though. We can pull it from above, knowing that the derivative of 2u is 12, and knowing that the derivative of 6r is negative 12, we get a result of 0. So you can do it independently, or you can derive it and calculate it appropriately. We have 4v minus u plus v over r, which was calculated above to get the number 10, or go thoroughly throughout, and as you can tell, this is probably easier than doing all of this, but all the work is there. Denominator times derivative of the numerator minus numerator times derivative of the denominator, all over denominator squared. Notice that's not the pattern I took for 4v. 4v is only done by finding the derivative of v and leaving 4 attached. Still giving me a result of 10. And the last one, combining all of them will give me 36. Or deriving each one separately and evaluating gives me 36. All right, I think we're done. If you found any mistakes in my algebra, please let me know. I think everything's good. I tried looking over and graphing and making sure everything was perfect. Your test will be next class on Thursday, December 6th. If you have any other questions, email me a time to stay after school. I hope you enjoyed, and I hope this helps. Thanks.